Hello everybody. In this session we will learn how to model a rigid frame culvert structure or a small span bridge. For this kind of bridge we can always use ADA's culvert generator. It will facilitate the procedure of building the geometry, assigning the sections and materials, and also ADA can automatically define the other kind of loads like earth pressure. So it is a very helpful tool to model this kind of structures. So like always, I will begin with a new project here. So you can define the project configurations here, and because we will use a concrete structure here, if you want you can change any of these default values here. For this project I will leave them as they are here. So to access the culvert generator of ADA, we can always go to Tools, Generators, and Culvert. So as you see here in this window, the first part we will select the type of structure or culvert. Here we have so many kinds and different kinds of rigid frame structures or culverts here. For example, you have this kind of culvert here, or you can even define the other ones like this one. We have this one as well with the bottom slab. So you can find any kind of structure that you want to design here in this list. For this project I will use this one, rigid frame on footings. So after selecting the type of structure here, we click on parameters, and here you can define the parameters of your structure. So here I will define all these dimensions for my structure, and ADA will build it automatically. So for the inner width, which is this dimension here, I'm going to define 18 meters of span length. Slab thickness BS will be 600 in the middle. So because I want my structure to start this hunch from the middle and end here at the both ends of the span, so I will define the length of the hunch here as 9 meters, and the section of the beam here, the slab here, is 1 meter, or the depth, so it will be 400 more than 600. We can also define automatically the footings. So here the thickness of footing I will use 1 meters, and for width it's 2 meters. In these two parts we can define the parameters about the legs. So my structure is symmetrical, so there will be same. For the HG of the leg or the height of the leg, I will put 6,500 millimeters. Maximum thickness at CG will be 1 meters again, and at the bottom is 750, and the inner footing dimension ZG is 625. So I'm going to use the same numbers for the right leg. Just copy and paste. Okay. So here I've defined the geometry of my frame. Click OK. And in this window, now we can select the types of material. So for this structure, I will use the concrete 030. And this is the width that we consider for our frame, that ADA will do the analysis and design based on this width of the frame. So let's say if the width of this bridge here or the culvert is 10 meters, here we only choose the first meter or 1 meter, so the design and analysis will be based on per meter of the width of the structure. So here I change just 1 meter, click just 1 meter. For the backfill, I'm going to just add 100 millimeters here. We don't have any slope longitudinally here. Unit weight of soil 22, it's okay. And these factors you see here is for soil structure interaction to apply the soil pressure to the structure. So these values I'm going to leave them as R. These are the number of subdivisions that ADA will generate for the vertical and for the foundation subdivisions. And for this final one is the geotechnical reaction at the SLS that we have. Normally we have this from soil report. So this one also I will leave it as is. And the final one is for seismic analysis that we don't do it here in this structure. So it will be 0. If I click OK here, and I'm going to save this project as Culvert 1. Okay, if you see and check it here, ADA automatically created my geometry. And if you see here for the foundation or bottom of the foundation, ADA calculated the spring elements here based on the soil characteristics. So if I go to 3D view and activate this 3D display, as you see, ADA has generated the just 1 meter width of my rigid frame here or culvert. And if we check it from the elevation view, as you see, this is the structure. And if we click on one of these members here, if I go to member mode, click this, you will see that ADA automatically defined everything. So it defined this section, dead load, self load, type of material, and everything is defined here. It has even defined your moving load axes, so you don't need to define them manually. The members is automatically aligned as top, and all of the other properties have been defined automatically. Even for supports, if you check, you can have the stiffness of springs here, as you see, Rx and Ry. They are defined as elastic supports, and here is the number of the value of stiffness for each spring. So ADA automatically has calculated all of these properties. The next step that we can do here is defining the moving loads. So if we use this moving load generator here, so click this, and this project I will use this S6 Ontario, and for transitory loads it will be normal level 1. You can always change this. It's a 2D structure, so it's technically it's a 2D frame, so I will use 2D moving loads. Axis 1 is already defined automatically. For traffic, I'm going to use both weights. Edit all, and other values, as you see here, all automatically have been selected with ADA. So I click next and finish. So here ADA generated all of the moving load cases. Click OK. You have also other kind of load cases. Some of them they are defined automatically. So ADA has defined some of them here, as you see, for example, the backfit pressure or dead load for the concrete structure or concrete frame. And if you want to add extra dead load cases here, you can always have that opportunity. For example, if I want to add a superimposed dead load, so you can just type it here, superimposed dead, and the type we can always use 6, let's say, a bearing surface. So, and you can have other kind of loads here if you want. So click OK. You can apply that load in the loading mode. So superimpose that load, say project yes, side view, select the slab members, okay, like this, using Control H. Now you can apply the load. I'm going to apply a load of apply a load of minus 5 kilonewton per meter for the bearing surface, parapet wall, sidewalk, and other stuff. So it will be added here, as you see. Okay. ADA has also automatically defined the design specifications for all of the members. So if you want to check them, because it's a concrete structure and we have continuous systems here, so you can always check the design specifications using these continuous members. Double click, for example, if you want to check the slab, and as you see, it's already assigned. The name is frame top, and it says slab beam, and you have other properties for crack control. You have the lengths and everything here. You can modify if you want. For example, if let's say we change the cover to 70 millimeters at top and bottom, and you can change the other properties. Also, if I check and click this here, as you see, ADA generated these 3 load cases here for my culvert structure here. So it's frame top, frame column, and frame footings. All of them are S6 2006, and you can change the code if you want here. ADA will design them to maximum capacity factor of 100. Here you can define your main reinforcement that ADA is going to use, the size. And also in this tab here you can define other kind of properties for the design. Okay, and you can also even check for this, and ADA is already assigned this frame column, and this one color covers are different, they're automatically defined. So as you see, it's really easy and fast to define the geometry and assign the properties of this kind of structure in ADA. The final step that we need to do here before doing the analysis and design is to define our load combinations. So I will use generator here. I will use this code S6 2006, and all of other default values are fine. Next. So we don't have seismic yet. We have moving loads. We arrange the envelopes here, so they will need to analyze, check to analyze, as it's already discussed in moving load training session. Right click, select the code, 6 2006, reinitialize. So right now my envelopes are defined and assigned to the load cases, and they will be included in the load combinations. So click next. Okay, you have everything. You have these dead loads, earthquake, the moving load. So clicking finish, as you see, ADA generated 29 load combinations, or ULSs, SLSs, or FLSs. Click OK. So right now we are ready to perform the analysis. So click here, analysis and design. Save the project, yes. Analyze. So calculation is complete, close. We need to always check for the summary here. So everything is okay, analysis, and the combinations, all of them have been converged. So to check the results, continuous system, double click. We want to see the results for slab. So as you see, ADA has designed it for the main reinforcements. So to check the results, I will go to view options or press O. So general and beam diagrams. So as you see here, you have the diagrams. And if you want to check for design, or firstly we need to add some sections, so it will help us to check out these rebars better. So cross-section generator 3 will be automatically generated. Okay, so these are the cross sections, these are the rebars in this part and this part. And if you want to check for design, as you see here, we have some yellow cells here. 88 flagged that we may have some problems with our design. So as I check here positive bending, we have all of these ratios here. So to correct the design or check for other stuff, we need to check all of the other for also negative bending and shear force. So as you see, for shear force, we need to add some stirrups. ADA normally doesn't design this kind of structure for stirrups because it's just 1 meter width of the structure, but you can always add stirrups and check for design manually. That's what I will show you here. So I'm going to define stirrups for this length of the slab here. To add the stirrups, we can go to bar replacement, transverse. So I will add, let's say, 15 M's. For example, these values just are approximation. You can modify them afterwards. Let's say if we want to add 60 of them from each 300 millimeters, and I want them to start a bit farther from the starting of the slab. So let's put it as starting from 600. Okay. And for the pattern, you can select each one of these patterns here. So because I want to have 2 legs, I'm going to select this pattern, but you can have also ties here, so you can calculate this section using the ties. In this example, I'm just going to use this bending shape, and here we need to define the coordinates of this stirrup. So for x direction, let's define it as -400 x left and x right 400. So it will be in the middle of section. And here for superior, let's put it from -70 millimeters to -500. So click OK. And as you see, ADA has placed the stirrups. You can see the section here. We have 2 legs. And here you have the elevation. And right now, if I check my design results again, as you see, all of the cells are white now. I have some problems here in the middle of the section that we can add a reinforcement there, but the other ones and the shear is fine right now. So to correct these yellow cells, we can add another reinforcement bar here, or reinforcement layer, or we can simply change these rebars the distance between them, or the size. You can do whatever. Here, because of simplicity, I just changed it to 45 M's. It's not practical, but here we're just showing how you can modify the reinforcements in ADA, but maybe the practical way is adding another layer here. So it's up to the designer. So if we change them to 45 m's, so you have much more stronger reinforcement here. And if you check for results, as you see here, everything is white and you don't have any flagged cells here or members, so everything is okay. I'm going to show you if you want to add an extra reinforcement here, you can just click. Let's say if we change this back to 30 amps, so to add an extra, you can just copy and paste it here. So the second layer I will use the same, and for this you need to define the coordinates of the second layer. So let's say we put it in minus 500 local YF section and start from 0Z. The ending also will be minus 500. And let's say it will be 18,000, the length of span. This will be order 1, order 2, and continuous. Click OK. So as you see here, I've added this bar of reinforcement here. So you can see it here. You can modify the direction. You can define the reinforcement exactly as same as here, sloped one, or you can even bring it higher or lower. So if here I put minus 400, ADA is calculating again, and as you see I have the distance here, cross sections here. So you have different ways of placing and modifying reinforcements in ADA, and whenever you change anything in reinforcements, ADA automatically recalculates everything, and it will show you that if your design is alright, it's passing or no. Okay, yes, and you can also check for the legs here. You have all of this information here. Like I mentioned before, you can add extra reinforcements or stirrups. And also if you want to check for the foundation here, the footing, you have it here. So these are the reinforcements, and you can add cross sections manually. So if I put it as 1000 millimeters, it will be the middle of the footing, and you can move this section here by clicking it and bring it down here. So this is the section for my footing. I will have the slab, we may have some problems with shear. If I check the results for shear, yes. And as I already explained to you, you can add the extra stirrups here. to make the foundation stronger against the shear force. Yes. This was a simple model on modeling a culvert and designing it in ADA. And as you see, it was very fast and efficient. You had all kind of the loads and load combinations. The geometry is already generated easily. So this is one way to model this kind of structures. We have also other type of elements, which is finite element plates. We can use to design this kind of structures, I mean the concrete slabs. In the next part, I will show you how to model a culvert using finite element concretes. In that case, the model will be completely 3D, and you will have the results for stresses, reinforcements, and all kinds of other results, deflections for the structure, and it will be more detailed because it is finite element modeling. So to start my finite element model, I will start a new project, 3D view. So first thing is to start a model. So always new, I will add 4 nodes. Or let's use the spreadsheet. So the first node will be 0, 0, 0. Node number 1, node number 2. Let's say it is, we have the width of the slab is 10 meters. 0, 0, Z. 3. So other corner of the wall, let's put 6 meters height for the rigid frame, and the fourth number here, 0 and 6. Okay, so I have the 4 corner nodes for my wall. Next stage is to define a finite element plate here for my first wall. So add, so as you see it's here. This is the dialog box for finite element plates. Here you can define the characteristics. So for thickness, for example, I'm gonna enter 750 millimeters. Material will be concrete 0.30. For dead load, let's use dead. It's not a rigid plate. No eccentricities for the wall. To have this the reinforcement design, you need to define an orientation system for the wall. So here we click this icon here, and we can define a new orientation system and specification for designing the wall reinforcement. So add, I'm gonna name it as wall 1, and this x-axis and y-axis that you see here, these are the local coordinates of the plate. So here for my wall, I want my local x coordinate as just same as my global x, so I will put 1 here. And also my y coordinates, local y, I want it to follow global y. So I will change this to global y1. So my plate here will have a local x-axis exactly in the direction of global x, and local y again following the global y here, 1. For specifications, you can click here if you have designed them before, or if you have them. If you didn't define specifications, you can always click this icon here and define it, as I've already explained to you in previous sessions. So here I'm gonna use a 6-6 design. For the cover, top and bottom, I'm gonna change them to let's say 60 millimeters. And for lateral also 60. Click OK. And right now we are going to assign this orientation, wall 1, to this plate. Here is the behavior tab. So we will have shear and torsion bending. It's a plane stress element. And here, as you see, these are the other characteristics of this plate. So for now we don't have any moving loads on the wall, so it's not required. Click OK. So the wall is generated. The other activity that we need to do here is to divide this plate, because if you use this kind of finite element plate, it's too large and you will not have correct results on that. So we always need to mesh the finite element plates to smaller amounts. So select it. In the tools menu, we have plates and split. So here we have a rectangular plate here, and I want to divide it by let's say 20 by 20. Okay, and here 88 divided this plate. To build the other wall, we can just use the copy and paste. So select all of the members, Control C, Control V, Control C, and in Z direction, let's say our span is 18 meters. Okay, Control V. So as you see, the second wall is copied here. The only thing that we need to change here is to define another orientation system for this. So we can select these members, Control H, to have the properties. And if we check for the orientation system, we need to define a new one as wall 2. So click here, add wall 2. So it will be the same. X will be, local X will be according to global X, and local Y will be according to global Y. So this one will be 0. Same as 2006 design, and same values, 60 millimeters. Okay, and here for these walls, I will assign wall 2. Okay, so if you click one of these members here, shells, you will see that wall 2 is already assigned. So I have generated the mesh for my legs or walls. The next step is to generate the slab. So same thing, add a slab. I will start from this corner node here, this one, and this one. So this is the slab. For a slab also, let's use the same thickness, same material, dead load. We need to change the orientation system because it's different here. So add a new one. I'll name it as slab. So in this case, my local X, I want to use it as a global Z. So here, one. And my local Y, it will be at X, global X. So you can check it again. Your local X for the plate in this direction will follow global Z, and your local Y in this direction will follow global X. One here. And here we defined a 6 again, and let's use the same covers for the slab also. Okay, assign it slab. So other default values are fine here. We can also add a moving load to the slab, moving load axis. So let's say it will be JK. Firstly, we check for the moving load axis. Yes, it's okay. And next we need to mesh this member also, mesh this plate as the others, but make sure that all of the nodes from your mesh on the slab should coincide with these nodes, and ADA will automatically merge them. So I will use the same 20 by 20. Select the finite element plate, tools, plates, and same 20. Click OK. Okay. The moving loads also, the axis also has copied that we don't want them to happen. To remove that from the other ones, we can go to up view here, select the other plates, not this one, because for this one I want to use the axis. For these ones we don't want them. Control H, and in rectangular we can remove the axis one from those. So replace and not required. Okay. Also here we have no position for that, so it will be not applicable. Okay. And right now if I check for moving load axis, as you see here, that's only one, as we have already discussed about it in 3D moving load application. So right now the geometry of structure is done. We have assigned everything to finite element plates. You can check for their thickness from attributes, plates, 3D display, and as you see, all have the equal thickness. If you have a frame or culvert which has variable thickness, You can always select the elements. For example, select this elements here and change their thickness according to your model. So in this example, I'm just going to use the same thickness for all of the members. We need to add our supports. So let's select these nodes here. The bottom nodes on the wall. Looking from side is easier, okay. Node selection, select the nodes, okay. Control H, we will define them as supports, okay. So these are supports, and if you want to release the rotation around global X, you can select the slab, the supports, Control H, and release the MX. So you will have hinged supports at the bottom. Okay. In this step, you can add load cases. Define that the load is already here. Let's say we add another load case as superimposed. And 6 surface. Also, you can add soil pressure or other kind of loads. And in this example, I'm not going to use the soil pressure, but you can always add it like the example before. So click OK. Add superimposed loads. Say project advanced 2 as FE slab Culvert. So to add the loads for a superimposed load case, select all of the finite element members for the slab. Control H. Let's add -5 kilopascal. And projection, let's use it global. Okay, so as you see here, the loads are also applied to finite element model. After this, we can define our moving load cases. Loads, moving load cases. I'm going to use the generator. Using Ontario code, normal. It's a 3D project. Axis 1 is already defined. Traffic's 2 base. Delete all existing. And to X1 and X2, as I've already explained to you, it depends on the local axis of your axis 1 member here. So X2 will be this dimension here. Let's start with 9 meters, and X1, let's start it from 1 meter. We can use this simultaneously loaded lanes. So let's say in this project we have two lanes simultaneously loaded. So if we click next, ADA has generated the load cases. Finish, they are here. So click OK. If you want to view the moving loads, so elements, so you can view all of them. Like here, as you see, it's starting from the edge of the bridge, and here we have two lanes loaded. So this is just for an example. You can modify the moving load cases from here in this dialog box. Okay, and the final step, as always, is the load combination. So load combination generator. We will use a sticks. All others are fine. Next. So we have moving loads. We need to define, activate the analysis and define the code. So 6 reinitialized. Okay, next. So the moving loads will be included in our load combinations. Click finish, and you have the load combinations here. Click OK. Right now we can perform the analysis and design. So click analysis and design, start analysis. It may take a while because we have finite element plates there and moving load cases 3D. So both of those elements causes the analysis to take much more time. So here AD started the design, and now we have the calculations complete. Close. So check if everything is converged. Yes. Okay. Right now you have the you can check the results for the finite element plates. So I will remove this here and also remove this check mark to have 2D view. And if you want to check for results, let's say on ULS1 on finite element plates, go to view options, finite element results. Let's check for sigma maximum. Okay, so as you see here, these are the stress values for the finite element plates for this load combination. Also, you can check for other results here, sigma minimum. Bending MX. And also you can check for shear or all of the results you have available here for your finite element plates. You can also check for deflection. So I put it down here to have better view. Okay, this is the deflection. For this load combination also you have this deflection here. As you see here, my supports are hinged. You can have the numbers by clicking on the plate. So if you want to check the number here, the deflections are here, minus 15 millimeters, and you have the internal forces here for that clicked element. And also ADA have designed the reinforcement for all of the finite element plates. To check for the design, you need to just click on your placement window, and here you have all of the orientations here. You can have them all or check one by one. For example, if you want to check the reinforcement for slab, just click it here, and you can use these icons here to view the rebars in any direction, in top layers or bottom layers or both of them. So for example, if I want to check this direction here, you have these rebars in this direction, and also you can have this. So as you see, if I check it 3D, you will see we have at the bottom 20 Ms and 15 Ms, and at the top in this direction we have just 15 Ms. And also you can check for the other direction, so just click this one and this one, and for longitudinal direction you can check out the reinforcements here. This is the bottom, this is the top. In top we have much more reinforcement. So these were the reinforcement for the slab. And also if you want to check the reinforcement for the wall, you can just click here. You have these top and bottom layers here, 15 Ms and 20 Ms, and you can have the other direction. As you see, we have much more reinforcements here because of the moment on external face. And you have the results also for the wall too. Both directions. So this was another approach to design the reinforcement for culverts or rigid concrete frames in ADA. You can use both of them. It depends on the decision of engineer. But as you see, there are so many features in ADA to model and design these structures. I hope this session was helpful for you. And if you have any questions, please send us an email in our email address here. Thank you very much.